These days, air power is the key to winning battles. But fighting on your own doorstep is one thing. Fighting a war on the other side of the world is another. So how do you do it? Well, you're going to need one of these. An aircraft carrier.
In a modern navy, an aircraft carrier is the most important warship in the fleet. It's a floating airport, city and battleship all rolled into one.
This aircraft carrier is a fearsome warship and a technological marvel, but it's only possible thanks to some unlikely engineering legacies.
The power of a hearing aid.
It was doing its job.
There's a very good chance we might all surprise me.
A boomerang.
No, there's not.
An agricultural seed drill.
Nothing would have gone through that.
One of London's most famous landmarks.
2, 1.
That was a lot of energy in one hit.
And the space race.
Illustrious, one of the Royal Navy's invincible class aircraft carriers. She's a floating air base for Harrier strike aircraft and helicopter squadrons. And keeping this whole thing operational 24 hours a day in a war zone, it's not easy.
When an aircraft carrier sails to war, it takes a whole battle group of destroyers, frigates and supply ships with it. Its primary role is to launch combat aircraft to strike enemy targets hundreds of kilometers over the horizon. And to achieve that, it's crewed by over 1,000 men and women who live and work within the confines of the steel hull.
Below decks, an aircraft carrier probably looks and feels much like any other warship, but its main role, of course, is very specific. Its job is to be ready for its aircraft to land or take off at any time. And that means it's very important to keep the deck level. I can understand how it'd be a bit tricky if the deck was being tossed about violently on a rough sea. But in fact, if it's any more than 5 degrees off the horizontal, nothing flies.
And that's not much use if you need to fight wars anywhere, anytime, and in absolutely any sea condition. Illustrious weighs 22,000 tons. She's big. And one of the biggest challenges is to keep her flight deck level at all times. The best place to observe this is from a helicopter. Not a problem on an aircraft carrier.
Come up here and suddenly your sense of perspective undergoes a subtle shift, because yes, an aircraft carrier is a very, very big thing, but so's the sea, and it's easy to imagine how she could be thrown around all over the place by a rough, violent sea, and yet somehow Illustrious seems to sail on serenely regardless. How does she do that? Well, largely thanks to 4 stabilizers, 2 at the front and 2 at the back, and they sort of fly her through the water, and they all come courtesy of the boomerang.
Hugh Hunt, a full-time engineering lecturer at Cambridge University and part-time boomerang expert, should be able to show me why.
Hugh,
Hello, Richard.
I've brought my boomerang.
Very good. You call that a boomerang?
Well, that's what they said when I bought it. Yeah.
No, this is a boomerang.
Well, that doesn't look anything like this.
Well, yeah, you can sort of imagine, if I've got a couple of ordinary boomerangs like this, you can imagine stick 2 of them together.
Yeah.
And it's sort of X-shaped like this one is. And, you know, the original boomerangs from, you know, Aboriginals and so on were boomerang shaped, but we can make them more efficient and more interesting if we do them like this.
So you're going to teach me to throw one? Do I learn with that one?
You could, but no, I'm going to give you a beginner's boomerang here. This is more your size.
That's it.
That's it.
Okay, fine. I'll put my boomerang down there and I'll use yours.
Yeah, right.
What do I do? I've never done this.
Right. So, yeah, well, you find the wind sort of that way. So you go 45 degrees around to the right of the wind. Right?
Yes.
And in a vertical, up and down, vertical plane, you throw the boomerang. Now you've got to give it lots of spin.
Here we go.
There we go. So give it a good spin. There we go. It comes back. Catch it. Hey. What were you doing? You weren't watching.
Concentrating. Wow.
You could have caught that one.
So, let me just do this once more.
Yeah. Okay.
And then ask what's actually
right.
happening. Because why does it do this?
Right, well, this is behaving like a gyroscope. Now, the gyroscopic effect is really pretty interesting. Whenever you have a spinning object naturally would like to stay spinning about a fixed axis.
But it's only when you make the blades wing-shaped that it returns. That aerodynamic design causes the boomerang to curve as it spins in flight.
No?
You're going to throw that?
Yeah, I'll give it a
you
go.
might kill a man.
It's quite light, made of balsa wood, you see, and it's fairly flexible.
I think that's probably for the more advanced boomerang.
Yeah, right, well, I'll give this a go, and, all right, here we
There's
go.
a very good chance we might all survive this. No, there's not.
Without an aerodynamic design, a boomerang would just spin in the vertical plane and fly in a straight path. And then there's the gyroscopic effect. It's this effect that helps to make the boomerang stable and accurate over a long distance. The faster a boomerang spins, the greater the gyroscopic effect. It's what made original boomerangs great for hunting.
This is a handmade Australian boomerang, and it actually isn't meant to come back at all. It's much more like a hunting boomerang than this fun returning boomerang. So I can throw this, and this is going to go way over there.
So you select your prey and you throw that out?
Well, the idea really is, imagine you're hungry, right? And there's a flock of birds.
Yeah.
And you could creep up on them, maybe, but they'll fly away, right?
Right.
So you could throw a rock. But if you've got something like this, which has got a bit of aerodynamic lift to it, then you can throw it further, spinning like mad, and moves around, and your flock of birds is...
What? And you're hoping to hopefully hit a bird with it?
Really, I just want this to get there and startle the birds, and they're going to take off, and hopefully I'm going to take one out.
What, hit a bird with that?
Yeah, that's
ambitious. Go on then.
Well,
you hit three.
Of course, this gyroscopic effect is not limited to just boomerangs.
I'm going to grab one side of that tray for me. Right, let's get this spinning top going. Now that wants to stay spinning about the axis, and we can tilt the tray.
Oh, I see, yes.
And it still stays
It wants
spinning.
to stay level, yeah.
It'll stay spinning about the same axis.
It doesn't matter what we do with the tray. The top stays spinning in exactly the same upright position. And it's this behaviour that allows the aircraft carrier to keep its flight level. To show how it works, I've built my own gyroscope, a spinning disc free to rotate in any direction.
It is important to remember, isn't it, that it's not moving, we are.
Just like the spinning top, it stays spinning in the same axis. However, the truck moves underneath it.
So there it goes, it's turning around. At least to us it's turning around. But it's not turning around, it's the truck that's turning around. And so we're able to detect our motion relative to that.
So in other words, it wants to stay exactly where it is, doing what it is, in space. And we are now moving around it, but it stays where it is.
And by being able to measure the difference in movement between the gyroscope and truck or ship, we can compensate for that movement.
And here, on this battle-ready aircraft carrier, the gyroscopic effect is put to a very specific use in keeping the whole ship stable so that aircraft can operate from the flight deck in pretty much any sea conditions. This is the ship's gyroscope room. In here, apparently, there are two different gyroscopes. Simon, I can't find them. Am I standing next to one?
Yep. First one here, naval compass system, has two separate spinning gyros in it, like the ones you've seen. One in this plane, one in the horizontal plane. spinning at 11,800 RPM. As the ship moves around, obviously they're staying stable, and we're using an electrical system to measure off the degree of pitch, roll and ship's heading.
The gyros on Illustrious spin almost 8 times faster than the one I built. The faster a gyroscope spins, the stronger the gyroscopic effect and the more stable it is, so the measurements taken from it are very accurate. As the ship pitches and rolls, this information is fed directly to the stabilizers, and they adjust accordingly to maintain a smooth trim through the water and keep the flight deck level.
So thanks to an ancient hunting boomerang, an aircraft carrier today can keep its flight deck level, ready for its aircraft to take off at just a moment's notice. But how do you launch a squadron of jets in just a few minutes?
Illustrious is a potent force with a powerful punch. In a war zone, the flight deck is a buzz of activity as jets and helicopters are readied for action. But not all the aircraft can be kept on the flight deck ready to roll. Some are stored in the hangar below and need to be moved up to the flight deck as quickly as possible.
And that's where these come in. 2 massive aircraft lifts, one here at the back, the other up at the front. Each lift weighs 70 tons, and it can move the 3 levels between the hangar and the flight deck in just 36 seconds. And that speed is important because, well, when you're fighting a war, you want to get your aeroplanes up here to the flight deck and in the air as quick as possible. And that's where traditional engineering struggles.
The aircraft lifts are hydraulic. Most hydraulic systems on their own are powerful but slow, and although they could lift the aircraft, it would take far too long.
These devices provided a solution. They're called accumulators, and, well, they don't look like much, but they can greatly increase the pressure in a hydraulic system, and that can speed things up. So it's thanks to these that lift can get on with its job, and it can do it quickly.
A 19th century engineer, William George Armstrong, invented them. More famous for manufacturing guns, he was also into dockside hydraulic cranes. These were powered by water, but mains pressure at the time was low and often unreliable. So Armstrong devised an entirely new way of creating high pressure within a hydraulic system.
And Armstrong's device, the accumulator, was used to its biggest effect on one of London's most famous landmarks, the Tower Bridge.
At the height of Britain's industrial power, London faced a problem. The Thames docks were home to large commercial shipping, which needed access upriver, but the growing population needed bridges. The solution was a bridge with 2 lifting roadways, or bascules. People and traffic could cross, but when shipping needed to get through, the bascules could be raised.
Each of the carrier's lifts can raise 85 tons. Each of those 2 road sections, bascules, weighs 1,200 tons. And speed was important too, because when the bridge was first opened in 1894, it was raised over 6,000 times in that first year. That's once every 20 minutes in its operational hours.
And it's the accumulator that provided the hydraulic pressure to do this. At the time, they were amongst the biggest accumulators that Armstrong had built. But today, the bridge is all electric.
I'm down in the depths of one of the towers. That's the bascule up above with the road going across. And from time to time, you can hear the thump of the traffic crossing overhead. When the bridge is raised, that pivoted counterweight, everything you can see painted white up there, swings down through this cavernous chamber. Probably best if I don't hang around too long here. And this is one of the old accumulators still down here in the base of Tower Bridge. I say one of them because there were originally 6 as part of the hydraulic system. As you can see, they are quite large. Each one weighed 100 tons and had to be able to move up and down within the chamber. That's some serious Victorian engineering. They did love a big bolt and a rivet, didn't they?
Serious Victorian engineering they may be, but they still have modern applications, and there are contemporary engineers who know how to make and use them. People like Geraint Owen.
Right, it's time finally to get to grips with accumulators and find out just how they work. Geraint, you've built one. Well, you say you built one. It's just some pipes and a foot pump.
It is largely some pipes and foot pump. We've got you a bit of a mock-up of your tower bridge, and you've got a little stirrup pump and a bucket of water, just to give you an idea of you pumping up the bridge, because you're doing all the hard work, as imagining there's a boat coming. So if you get pumping, we can see the bridge opening.
So this is the bridge.
Yeah.
Ship's coming along, and this is just with a pump to open the bridge.
Yeah.
Right. That's working. I'm pumping the bridge up. There goes tower bridge.
And eventually your hard work is leading to the bridge being open.
Yeah.
So it's simple hydraulics. You've got a pump, you've got a ram, up it opens.
Yeah. So what difference does an accumulator make?
The trouble is that you've been doing that sort of in real time, and it can only open as fast as you can pump.
Yes.
Whereas if we, instead of opening the bridge, we get you to to put the energy into an accumulator, which we've got an accumulator here. So if you get pumping again, we can use the same amount of energy and put it into this accumulator. So you pump away merrily. Here we've got some weights onto a hydraulic ram that's keeping the water under pressure. That's probably enough. So that's now there. It can stay there. The energy is being stored. Anytime we want, we can now open the valve and open the bridge. So here comes your boat. Open the valve.
And just in one smooth stroke, the thing's open.
Same amount of energy.
But it's stored in there. It literally does accumulate energy then, and keeps it for when you need it.
Exactly that. So it's just kind of a battery for hydraulics to store some energy.
So an accumulator stores energy, ready to be released the moment it's needed. The more accumulators a system has, the more energy it can store, and the faster it can work.
On Illustrious, each lift has 4 accumulators. They can boost the pressure of the whole hydraulic system up to 172 bar. And if you consider that your average car tyre is at just over 2 bar, you get a sense of the energy stored in it.
A model of the bridge may demonstrate the principle of accumulator power, but I've devised a test that'll take things a little further. Well, a lot further. I'm going to find out how quickly I can move a car along an inclined trailer using just a 62 horsepower engine driving a hydraulic pump. I'm then going to use the same engine and pump to charge an accumulator. And then let's see what happens when I release the energy from that. So I'll need a bank of accumulators.
There are half a dozen of these, which are the sort of modern design of nitrogen-filled accumulator.
Modern accumulators contain a bladder, like a heavy-duty balloon, which is filled with high-pressure gas. As hydraulic fluid is pumped in from the bottom, the bladder is squeezed, storing potential energy. When energy is then needed from the accumulator, a valve is opened. The compressed bladder very quickly expands back to its original size, forcing the hydraulic fluid out under extreme pressure.
So it's accumulating that energy, which is the same, but rather than lifting a weight and holding it, and there's the potential energy in that lifted weight that can drop, it's actually compressing.
It's squashing the nitrogen.
And that wants to come back to its full volume, and that's where the energy is stored. So it's the same system. Okay. I guess we're going to do this first without the accumulators.
You've got it right.
I don't have to pump, though.
No. All we've got to do is get the engine started.
Can we fire up the engine? Thank you, Adrian.
Using only the engine, the hydraulic pump creates a constant pressure of just over 1/4 of a bar with which to drag the half-ton car. It moves, but it's slow. It's the equivalent of me pumping the model bridge with the stirrup pump on its own. But by charging the accumulators instead, we can build up the pressure and store much more energy.
We can, and we might be able to put a bit more in as well.
Wouldn't that be awful? What if we stored quite a lot more energy than we actually needed in there, and then deployed it all in one big lump? Is it just me, or is that machine really quite terrifying?
There is a great deal of energy being stored up in the accumulators, so
Yeah.
there's an inherent danger, I suppose.
Good. Well, you've confirmed on my way.
Charging the accumulators for just 10 minutes creates a pressure of 241 bar. That'll provide the same energy as having 23 of these engines pumping at once.
Right, okay, if we're ready, everybody, this is it. Live firing. 3, 2, 1.
That was a lot of energy in one hit. I mean, all in one lump.
That certainly worked, didn't it?
Yeah, it did. Probably in the interests of science and engineering, we should
go and examine the damage. Yeah, come on, let's go and have a look.
Behold a flying car, thanks to the instantaneous accumulator energy.
Well, that's pretty tired, isn't it? I've seen worse.
So a connection with the Victorian bridge puts modern jet aircraft into the air in just a matter of minutes.
It's easy to see how powerful lifts and sophisticated stabilizers are essential to let an aircraft carrier do a job. But the business of keeping those aircraft flying is a hugely complex business, and it raises many, many demands, some less obvious but no less critical. And one of those demands is the need for water. Not that kind of water, obviously, fresh water. And Illustrious needs a lot of fresh water.
Illustrious gets through 200,000 litres of fresh water a day, and at that rate she can only store 2 days' supply. It's not just for drinking, more importantly it's for keeping the aircraft and machinery clean and in tip-top fighting condition.
3, 2, 1, ignition, liftoff, 30 minutes after the hour.
And it's this need for fresh water that connects the aircraft carrier to the space race. If it's a problem getting hold of fresh water halfway around the world, imagine what it's like halfway to another world. That's exactly the problem NASA faced in the 1960s and 70s during the space race with the Soviet Union. The early Gemini and Apollo space missions took fresh water with them, but for long-term space travel and survival, that just wasn't going to be feasible. An answer was found through reverse osmosis, a purification process that can make fresh, drinkable water.
To use reverse osmosis, you need to understand the pressures involved in osmosis.
Osmosis is the movement of water through a membrane. It's fundamental to life on Earth. Plants draw moisture through their roots using osmosis, and it's the way all living things maintain their cell structure.
In two neighbouring solutions, water will always flow from the weaker to the more concentrated solution. So from fresh water, say, to salt water. That's osmosis. It's what it does. Water molecules will continue to flow until the concentrations are balanced out.
Inventor Frank Pryor has a novel way of showing it. These eggs have no shell. They've been dissolved in vinegar, leaving just a membrane underneath.
So this is the sort of rubbery membrane that we've all encountered on an egg, on the inside of the shell.
Yep.
So there's no actual osmosis happening yet?
Not yet.
Okay.
Not yet. But if we take those and we pop one in water here and one in syrup here, okay, and then we leave them, we'll see what happens.
All right. So this goes in the water. Just pop it in there like that.
That's like so.
Okay.
And that one there, just pop it into here, okay? And then we leave them for a little while because osmosis is a slow process.
So these are going to do some osmosis?
Yep.
Okay, what is this? Is this a recipe?
Well, here's two that we prepared earlier.
Here's a recipe.
There we go. And as you can see, first of all, if you look at the one in water and you compare that to the size of the ordinary egg, it's enormous. That's right. And what's happened is water has moved from the outside into the egg to the sort of limited stretch of the membrane.
But in the other jar, the syrup is more concentrated, so the water has flowed out of the egg, leaving it shriveled.
So it's still osmosis, it's just coming out into the more concentrated solution, which here is outside rather than inside the egg.
Correct.
And as a result, it sort of collapsed and shriveled up.
It may be simple to see how osmosis occurs in nature, but how exactly do shriveled eggs connect the aircraft carrier to the space race?
In the 1960s, the Kennedy administration asked American scientists
to find a way of producing fresh water in salt water. Originally, it was for the greenification of deserts, but NASA realized very quickly how useful it would be to their astronauts.
It would allow for longer missions and put them ahead in the space race with the Soviet Union. Up until that time, extensive distillation was the only commercial method of artificially producing fresh water. However, scientists at UCLA had come up with a novel and much cheaper solution. They realized that water molecules are the smallest objects in an aqueous solution, much smaller than salt, bacteria, and even viruses. So they designed membranes with microscopic holes that only let pure water molecules pass through. All they had to do was force an aqueous liquid through this membrane, and in theory, all that would come out the other side would be pure water.
But there was just one problem: osmosis. We've already seen that water flows naturally into a concentrated solution, not the other way out of it. But what the scientists at UCLA were proposing was the exact opposite: reverse osmosis. They'd have to physically pump the concentrated solution through the membrane against the force of natural osmosis that wanted to force it the other way.
The good news for those on an aircraft carrier is that there's water all around. Unfortunately, it's not the fresh water vital to maintain the aircraft or refresh the crew.
So this can make drinking.
This could make drinking water from seawater.
Okay.
Yep. Okay. That's the membrane you use.
Wow. That's the actual...
That's the actual membrane.
I can't see the hole.
You won't.
But that's what it is, isn't it? That's basically just full of holes.
It's full of holes.
How small are these holes?
These holes are 0.5 of a nanometer. Okay. If you take a hair, that's 72,000 nanometers. Come down to bacteria, it's about 10,000 nanometers. Come down to virus, coming down to 100. And this is half. They're very, very small holes.
So it's fiddly to make this membrane, but once you've made it, that is, I'll have to take your word for it, full of holes.
That's right. It's wrapped up in the coil inside here, and you put a pressure on one side, and you just simply push through.
So, to replicate the problem faced by Illustrious, I need to make my own seawater.
Yeah, it's revolting. It's salt water.
You wouldn't like to drink too much of that,
No,
would you?
no,
No,
not at all.
Okay, well, let's convert it into drinking water.
You put this bucket down on the floor.
What a good idea.
Out of the way. Right, so that's our seawater in there. That's
fine.
Imagine the sea.
Okay, so just pump this up and down about every 2 seconds. Okay.
Right.
Slowly, and we'll get fresh water out of here.
You hold the little pipe, I'll do the work. Okay. Just down. 1, 2. Up. 1, 2.
That's right. Just slowly going. You can see it coming through the tube here.
I can see how this could work on an aircraft carrier, but I can't help thinking that there isn't much seawater in space.
There, in actual fact, you have to purify not seawater, but faux urine, because water is at a real premium there.
What? So you can put...
You put your own urine in and clean your... Yeah.
Thanks for not making me do that.
That's okay. We'll see you later.
It's one of those things in principle. Good.
Yep.
Great. Good principle.
Okay. I think that's enough to give it a try, don't you think?
So we can this is our drinkable water now. Now this is this was the same
That's horrible salt solution.
Okay.
So
you like a dram? There you go. I'll have a wee drop in
that's good.
Okay.
Cheers.
Cheers indeed. It looks. I'm letting you go first.
How's that?
Well, as far as my taste can tell you, that's just clean water. That's pure,
really quite amazing.
Pure water made from that horrible salty solution by producing twice the osmotic pressure to force it back to the membrane and leave the salt behind.
Yeah.
That is very, very clever.
Cheers.
So, it works, and reverse osmosis has been used for desalination since the 1960s. But by the time NASA developed a workable system for use in space, they'd already put a man on the moon. Today, however, it is used on the International Space Station. And on Illustrious, it's the only way to produce the 200,000 litres of fresh water that's needed every day.
So, the space race and the fact that you can't buy bottled water on the moon means the sailors of HMS Illustrious can enjoy fresh water. But this is a warship, and fresh water isn't going to protect them from an incoming missile.
To counter hostile threats, an aircraft carrier has a wide umbrella of defences.
Ask any sports coach and he'll tell you, to win a game you need to be as good in defence as you are in attack. And it's exactly the same thing here. When an aircraft carrier goes to war, it needs some serious protection.
The carrier's aircraft provide long-range defence. If a threat gets past them, the escorting ships and the battle group fire anti-missile missiles. And if those fail, then up close there are flares, chaff and other decoy devices.
But what if a missile still manages to get through all those defences? Well, for the last line of defence, it's all down to this gun. If this has to fire and it misses, then it could be goodbye to the carrier and all aboard. Thankfully, though, this isn't any old gun.
It's a weapon system called Goalkeeper, designed to destroy anything that gets through all the other defences. It can track up to 30 incoming targets at a time, prioritising them and then destroying them with its 30mm Gatling gun. But the clever part is that it's completely automated. Having no operator makes Goalkeeper faster and more accurate. And Illustrious has 3, providing full 360-degree cover. But this lethal machine has very humble beginnings. A 26-year-old storekeeper and an agricultural seed drill. Nikolai Thomasin Foster from the Royal Agricultural College has a replica of an 18th century seed drill. It was the first machine to plough, sow and harrow all at once.
So it's a very clever machine. It's doing a lot of different things at once. The key bit is the seed hopper bit. Can we have a look at that?
Yeah, it's the seed hopper, but just at the bottom of the seed hopper is a very simple metering unit. So if we just stop, we'll just have a look at a little cutaway we've got here that we've put together. So in this cutaway, we just got a simple metering unit. So this is actually the axle for the wheels, and as that turns, it just actually drops out an individual metered bit of seed every 6th of a turn.
Can I have a look at that? So that's actually happening
as you turn it.
So gravity is bringing the seeds down into these slots, and that's
an individual metered unit. It's very, very simple.
Your horse is going to get bored standing there, Nicola, I'm sorry.
By the mid-1800s, seed drills were revolutionising farming in America. The storekeeper improved the existing design by adding gears, and he made his fortune. But that's not what he became famous for. 18 years later, during the American Civil War, in an attempt to reduce the number of men needed in battle, and so reduce fatalities, the storekeeper invented a gun that would change history. Inspired by the speed and ease that gravity-fed seed through hoppers on drills, he swapped seeds for bullets. Easy and fast feeding of bullets was important because Mr. Gatling had invented the machine gun.
Yeah, that's right. The 26-year-old storekeeper was Richard Jordan Gatling, father of the machine gun and designer of his eponymous Gatling gun.
Peter Smithhurst is Senior Curator of Historical Firearms at the Royal Armouries, home to a very early Gatling gun.
It's a .65-inch caliber naval Gatling, fitted on a heavy pedestal mounting which will be bolted to the deck of a ship, and the gun can be traversed quite easily using the handle at the rear.
Can I say, it is massive. It's really heavy. There's a lot of metal in it, isn't there?
This naval gun was made 11 years after Gatling's first, coincidentally by William George Armstrong, who I came across earlier as inventor of the accumulator. Now there's an engineering connection. Armstrong modified Gatling's original design, especially in the way it was loaded.
Gatling's first gun, which was patented in 1862, simply had a hopper on the side there where cartridges could be manually dropped in by hand.
So this is the link back to our seed drill, really, because this was gravity doing the job. Cartridges go in, fed down into the gun, and away they go. Slightly different purpose.
from that point on, obviously, but the principle up to that point is the same. The workings of the Gatling gun rely on simple mechanics, which made it such a successful weapon. And what sort of rate could this thing fire at then?
If you're starting out fresh, perhaps 400 rounds a minute, but it's a tiring operation, it's a heavy mechanism to operate, so my guess is 200 might be a more acceptable average.
Over 130 years later, Goalkeeper's gun is the most modern version of the Gatling gun. It may have improved specifications, but it still works on the same multi-barrel principle as Gatling's original. And on Illustrious, it's weapons engineer Harry Fenton's job to maintain and load it.
That's obviously a drill round, a simulated bullet, because obviously I can't hand you a real one.
I don't want a real one. It's massive, look at it! These are loaded in here and rattle up there to the gun.
Yeah.
And the idea is it can fire a lot of rounds. How many of these?
He can fire 4,200 a minute, which equates to 70 a second. So
4,200 of these?
Of these, yeah.
A minute. 70 of those a second?
That's right, yeah.
In the air?
So they can make quite a mess of whatever's coming in, missile, aircraft.
So this is a combination then of just putting up thousands of rounds, an unimaginable number of rounds in the air at any time, and accuracy. So the computers and the guidance systems give it the ability to prioritise, to pick a target and to hone in on it. But then it's just putting up this wall of rounds. What a terrifying thing.
Sadly, though probably quite understandably, the Navy wouldn't let me actually fire Goalkeeper.
So instead I've come here to this big, deep, safe quarry, because down there I want to see if I can understand a bit more about this combination, these two qualities, firepower and accuracy.
Dave Ward designs and makes powerful sniper rifles, and he's brought some along so I can try to replicate what Goalkeeper does.
Well, this is our AS-50 50 caliber semi-automatic sniper rifle. Basically, it's an anti-material rifle built for taking out helicopters, light armoured vehicles and such like.
Over what kind of distances can this thing be accurate?
Oh, 2,000 metres easily.
Right. So, accuracy, that's
accuracy,
what it's about.
Yeah.
Okay, well, let's see some accuracy then. That's an immensely powerful weapon and very, very accurate. Can't deny that. But what we need is some way of combining then that accuracy and power, but with the shotgun thing of having a lot of rounds in the air at the same time.
That's right.
How many guns have you got here?
We've got 5 rifles here altogether. And
I think there's a further development of this experiment to do. I think it's important. Right, we've got some more blokes to fire.
Stand by! Stand by! Fire!
So, Dave, I think we can agree that that combination of accuracy, power, and just number of rounds in the air was devastating.
yes, I think it would definitely spoil somebody's day.
Yeah, it would have done that. And that kind of, well, it's a good approximation of the whole Goalkeeper process. A lot of aimed rounds. So it's all about accuracy, power, and number of rounds in the air at the same time. Nothing would have gone through that.
Goalkeeper fires rounds at over 3 times the speed of sound, destroying targets at a distance of up to 2 kilometers, only a second or 2 from impact. So thanks to a young storekeeper and a seed drill, Illustrious has an awesome final line of defense against incoming threats.
Down here in the operations room of the carrier, these guys are on the lookout constantly for potential threats, searching for that little blip on the screen that tells them someone or something is out there.
But even with these high-tech defences, there's one threat that can remain undetected until it's too late.
It's something the Germans used to devastating effect during World War II. Magnetic mines, huge explosives hidden in shallow water.
Magnetic mines didn't need to come into contact with ships to explode. a change in the surrounding magnetic field can trigger them. This was usually caused by a large amount of metal passing above, like a ship.
Obviously, that isn't a real ship. It's my remote control aircraft carrier. But it'll do to demonstrate the principles, because hidden out there in, well, the paddling pool is a magnetic mine.
And to replicate the magnetic field of a steel ship, I've attached magnets to my wooden boat.
Okay, setting sail, here we go. Yeah, magnetic mines really were a huge problem.
And then the Navy got lucky. A mine was spotted as it was parachuted down into the Thames. This was it, the Navy's big chance to unlock the secrets behind Hitler's deadly weapon. As the tide receded, one officer, armed with some hastily made non-magnetic tools, went in to defuse the deadly device.
The mission was a success, and the magnetic fuse was rushed off to be X-rayed. By the next day, the Navy experts had cracked it, and their solution took inspiration from a most unlikely source, the induction loop hearing aid. In 1937, Russian telephone engineer Joseph Polyakov developed a new way to help the hard of hearing, the very first induction loop hearing system. It allows the hard of hearing to hear a clear, amplified sound, and today these systems are found in many public places. The principle is based on the relationship between electricity and magnetism. A microphone converts sound into an electrical current. That electrical current is then passed through a coil of wire. The current naturally creates a magnetic field. This is an induction loop. Any receiving coil positioned within that magnetic field will transform the field back into a matching electrical current. Once amplified, the original sound can be heard by anyone wearing a coil hearing aid, as long as they're within the range of the magnetic field.
But how can something designed to improve hearing stop the mines from exploding? Well, it can't. It doesn't. What it does instead is make the whole ship disappear. To mines, at least, and that's the important thing.
Alistair Ballantyne is an electrical engineer, and he's going to show me exactly what happens on a ship.
That is now replicating a giant aircraft carrier, a big metal ship moving across a magnetic mine. Brilliant, we can see what's happening. How do you stop it?
When a current passes through a coil, it generates a magnetic field. So to counter the magnetic field generated by the magnets, all we need is a coil with current going through it.
It's the same principle that Polyakov used in his induction loop hearing aid system. It creates our very own magnetic field. But to make the ship disappear to magnetic mines, the key is to create a field that cancels out the ship's natural one.
So all we have to do now is put an electric current through your coil,
yes,
generate that magnetic field, and wham. It won't actually become invisible in front of us, because if we could do that, it'll just be invisible to your magnetic sensor down there,
yes,
or more importantly, to your magnetic mine.
All steel ships have a natural magnetic signature, which can be measured during sea trials. Once this is known, engineers pass a current through coils inside the ship's hull to create an opposing magnetic field. This neutralizes the signature, and the ship becomes magnetically invisible.
Down here, deep in the hull, a 200-amp current is generated and sent out along coils running right around the ship.
And I hope it'll work on my model carrier too.
How confident are you that it works?
Very confident.
Really?
Well, yeah.
Well, I have not only another ship, I have another mine. What say we test it properly?
Wisely taking the precaution of retreating a safe distance.
So, your system is up and running.
Yes.
It's neutralizing the magnetic signature of that small ship.
Yes.
Underneath it is a magnetic mine.
Yes.
If I switch that mine on with this switch, nothing should happen.
Hopefully.
Because the mine doesn't know the ship is there, because your system is neutralizing its magnetic signature.
Yes.
I'm making this tension worse, aren't I?
Yes.
Yes, I am. Okay, right, well. All being well, nothing at all is about to happen. Now, that is just this system neutralizing the magnetic signature of that ship So it's not triggering the mine.
Yes.
It works.
Yes.
I mean, we know it works.
Well, of
You
course,
fit it to
we
real
should,
ships,
yeah,
but
yeah.
it works there.
Yes.
We should, just to prove the point,
Shall we turn it off?
if we were to switch your system off, all of a sudden the ship would have a magnetic signature again, and it would trigger the mine.
Yes.
Turn it off. You can do it. On a count of 3. 3, 2, 1. It was doing its job.
And warships use the same principle today to hide themselves from the hundreds of mines still lying on seabeds in current and old battle zones. And all thanks to Joseph Polyakov and his induction loop hearing aid.
HMS Illustrious might not be the new kid on the block, but she still proves that the aircraft carrier remains the unrivaled battle platform in the fleet.
And she wouldn't rule the waves without the boomerang.